Welcome to the second lecture of the fifth week of Lent term, and the plan today is to finish chapter 5. So last time we started with the last remaining topic in chapter 5, which is on Zn and its modular arithmetic. So let's recall what the Zn was. If n is any natural number, then the Zn is the set of all equivalence classes under the equivalence relation of congruency modulo n. And let's recall how this relation was defined. If a and b are any two integers, we say that a is congruent to b mod n if n divides a minus b. So we check that this is an equivalence relation, and the set of equivalence classes that you get under this equivalence relation is this set Zn. So this Zn is a set containing such equivalence classes where a is an integer. And last time we showed that in fact this Zn has exactly n elements. So there are n distinct equivalence classes that you get, namely the equivalence class containing 0, equivalence class containing 1, all the way up till equivalence class containing n minus 1. And then if you look at the equivalence class containing n, that will be the same as the equivalence class containing 0, and the equivalence class containing n plus 1 will be the equivalence class of 1, and so on, and it keeps cycling periodically like this through this list. So that's what Zn is, and we also looked at what the equivalence class of any element looks like. So by definition, the equivalence class containing a is the set of all integers b which are related to a under this equivalence relation. So it's the set of all integers b such that b is congruent to a mod n. And last time we saw that in fact this set of b's is exactly the set of all elements a plus m times n, where m is any integer. So this set looks like this. It has these elements a plus n, a plus 2n, a plus 3n, and so on the one hand, and a minus n, a minus 2n, a minus 3n, and so on the other hand. Okay, so that's this set Zn of such equivalence classes. Now today what we'll do is we'll develop a modular arithmetic in this set Zn, by which we mean that we will define these two maps, plus and dot. Both of these are maps from Zn times Zn to Zn. Plus is called addition modulo n, and dot will be called multiplication modulo n, and we'll see properties of these two maps. So here is the definition of addition modulo n. So this addition modulo n is a mapping plus from Zn times Zn to Zn itself. Now let's recall that Zn is the collection of all equivalence classes under the equivalence relation of congruency modulo n. So I want to know how, given an equivalence class from here and an equivalence class from here, I can add the two. So let's take this equivalence class. Okay, so denoted by this orange box. So that's a set, and it has a lot of members. Maybe there's a member a, and then a plus n is there, a minus n is there, and so on. So this is the equivalence class containing a, but it's also the equivalence class of any of the members of this set. So equivalence class of a minus n, equivalence class of a plus n, and so on. So suppose you have another equivalence class from this set, this blue box, which is this set, and it has lots of elements. Maybe it has an element b, then it also has b plus n, b minus n, and so on. So this is the equivalence class containing b, but it's also the equivalence class of any of the members of this set. So it's the equivalence class of b plus n, equivalence class of b minus n, and so on. Now I want a recipe for adding this equivalence class with this equivalence class, and the recipe is as follows. You take any member from this equivalence class. Okay, so suppose I take a, for example, take any member from this equivalence class. Suppose I take b, for example. You add these two integers, so you get a plus b, and then you take the equivalence class of that element. Okay, so the equivalence class containing that element, all the elements which are congruent modulo n to this element. So that's an element in here. And now comes the question of well-definedness. After all, the instruction given is you take any element from this set and any element from this set, and you add the two, and then you take the equivalence class of that. But what guarantee is there that had I chosen some other element from here, not a, but maybe a plus 3n, and some other element from over here, which is not b, but say b minus 80,000 n, then if I add the two, I get some integer, and when I take the equivalence class of that, that I get the same equivalence class as the equivalence class containing a plus b. So that needs some checking. So sort of to drive the point home, here is what is happening. Let n be equal to 3 and I am defining this addition modulo 3. So I take any elements from Z3, okay, any two elements from Z3, say this equivalence class and this equivalence class. So these are sets. So this is the equivalence class of any of the members in this set. For example, 5 belongs to it, so it's the equivalence class of 5. It's also the equivalence class of 2, it's also the equivalence class of 11, and so on. Okay. And similarly, this is the equivalence class of 1, equivalence class of -2, equivalence class of -5, equivalence class of 7, equivalence class of 10, and so on. And we are giving a recipe for adding these two equivalence classes. The instruction given is you take any member from this set, For example, I take 11 and -2. You add the 2, I get 9, and then take the equivalence class of that. So I get this one. On the other hand, somebody else might have taken 311 and -5 and added the 2 and gets 306, and that person takes the equivalence class of this one. So for this to be a mapping, an unambiguous rule which tells you, given two equivalence class, what equivalence class is formed, it better be the case that this equivalence class containing 9 is the same as this equivalence class containing 306. So that's the question of well-definedness, and that needs checking. So let's check that. So suppose that you have an equivalence class which contains these two members A and A prime. So A prime is related to A prime is congruent to A modulo n. And similarly, let us suppose that the equivalence class of B and B prime are the same. So B and B prime belong to the same equivalence class. B prime is related to B. In other words, B prime is congruent B mod n. And then using this definition, to find the sum of these two equivalence classes, I might take A and B and end up with this equivalence class containing A plus B. And somebody else might take these representatives, A prime and B prime, and end up with the equivalence class containing A prime plus B prime. And so we need to check that at the end of the day, we have the same equivalence class, which is the sum of these two equivalence classes. So we have to check that the equivalence class containing A plus B is the same as the equivalence class containing A prime plus B prime. Now, these two equivalence classes will be the same if A prime plus B prime is related to A plus B. So A prime plus B prime should be congruent A plus B mod n. Is that true? And the answer is yes, because we know these two things. And last time we learned that if these two things happen, then if I add these two, the sum I obtain is congruent to the sum of these two mod n. So I add these two, and it turns out that the sum I obtained here is congruent to the sum I obtained here mod n. Okay, so because of that, we know that A prime plus B prime is indeed congruent to A plus B mod n. Okay, and so indeed, since these two are related to each other, their equivalence classes are the same. So this addition modulo n is a well-defined operation. We have defined addition modulo n in Zn, and now let us show that it has the properties of associativity, the existence of an additive identity, every element possessing a corresponding additive inverse, and the property of commutativity. And we know that the set of integers with integer addition has all these properties, and in fact we can use these properties for integer addition to derive the corresponding properties for addition modulo n. So let's begin with associativity. If you have any three elements in Zn, then we have this, that the sum of the first with the sum of the second and the third is the same as the sum of the first two added to the third one. Okay, so let's start with the left hand side, that's this, and then we have to add these two things. But by the definition of addition mod n, this is the equivalence class containing B plus C. And then again by the definition of addition modulo n, we know that this is the equivalence class containing A plus the sum of B with C. Now this is just integer addition, and we know that integer addition is associative, so we can write this as A plus B plus C. And then we work backwards. So again by the definition of addition modulo n, we know that this is equal to the sum of the equivalence class containing A plus B with the equivalence class containing C. And this thing further we can split into the sum of the equivalence class containing A with the equivalence class containing B. And so we have got this right hand side. So we have got associativity. And now let us show the existence of the additive identity with respect to addition modulo n. And that's going to be the equivalence class containing 0. Indeed, if I take any element in Zn, let us show that when to this element I add this equivalence class containing 0, I get the same element you started off with, and also in the opposite order. So let's start with the sum of the equivalence class containing A with the equivalence class containing 0. Well, by the definition of addition modulo n, we know that this is the equivalence class containing A plus 0. But this integer sum A plus 0 is just A, and so we have got this first part. And this A can also be written as 0 plus A, and then by splitting this using the definition of addition modulo n, we also have this other equality. So we have the existence of an additive identity, which is the 0 element. Now let us show that every element in Zn has a corresponding additive inverse such that when added to the given element at hand, we get the additive identity, the 0 element. If we take the element which is the equivalence class containing A, the integer A, then as its additive inverse, we have the equivalence class containing minus A. Indeed, the sum of these two is 0 because by the definition of addition mod n, this will be the equivalence class containing A plus minus A, but this sum is equal to 0. And so we have got this first part, and also this 0 can be written as minus A plus A, and splitting this again using the definition of addition modulo n, we get this thing. So we also have this thing. So every element has a corresponding additive inverse in Zn. And finally, we also have commutativity, because if you have any two elements, say these ones, then you have that this sum is also equal to this sum. And let's also quickly check that. So by the definition of addition modulo n, this sum is the equivalence class containing A plus B, but this integer sum A plus B is the same as the integer sum B plus A, since integer addition is commutative. And then we split this, and this is by the definition of addition modulo n, the equivalence class containing B plus the equivalence class containing A. Alright, so we have got this as well. So these are some properties possessed by addition modulo n. Here is the definition of multiplication modulo n. It's also a map from Zn times Zn to Zn, just like addition modulo n. And it takes a pair of elements from here and produces an element over here. Now elements in here are equivalence classes. So suppose you have the equivalence class containing A and an equivalence class containing B, then their product, which is denoted like this, is by definition the equivalence class containing the integer product of A and B. Now again, since this is a set, of course it has many other members too, and the instruction to calculate this is you take any element in here and any element in here and multiply them as integers and then take the equivalence class of that. So we have to check well-definedness of this multiplication, in the sense that if I take some other member from here and some other member from here and use them instead, then the equivalence class that I get at the end of the day is the same. So let us suppose that A is related to A prime, so that their equivalence classes are the same. Okay, so I have A and A prime belonging to the same equivalence class, and B and B prime belonging to the same equivalence class. Now instead of using the representatives A and B, if instead I use A prime and B prime, then this product at the end, which I end up with, is going to be the equivalence class containing A prime B prime. And we have to check that this equivalence class that we get is the same as the one that we get if you use some other representatives like A and B. Okay, so we have to check that A prime B prime is related to AB. That is, A prime B prime is congruent AB mod n. So is this true? Well, what we know is that since A and A prime belong to the same equivalence class, they are related. So we know that A prime is congruent A mod n, and similarly, since B and B prime belong to the same equivalence class, B prime is congruent B mod n. And then the question is whether these two together imply this. And the answer is yes, because last time we had seen this lemma which said that if I multiply these two and if I multiply these two, then it turns out that the product of these two is congruent to the product of these two mod n. So because of that lemma, we do have that A prime B prime is congruent AB mod n. So A prime B prime is related to AB under this equivalence relation of congruency modulo n, and so the equivalence classes are the same. So multiplication modulo n is well defined. Now let us see the properties of multiplication modulo n. So akin to the properties of usual integer multiplication, we have the following properties for multiplication in Zn. So properties of multiplication modulo n. You have that it is associative, there exists a multiplicative identity, and multiplication is commutative. But multiplicative inverses are not guaranteed to exist for every non-zero element. Okay, so let's look at these properties, and just like with the properties of addition modulo n, we will prove these properties for multiplication modulo n using the corresponding properties for integer multiplication. So first of all, with associativity, you have that for any three elements in Zn, you have that the product of the first element with the product of the other two is equal to the product of the first two multiplied by the third one. So let's start with the left hand side. Then you have this thing, and the product of these two by the definition of multiplication in Zn is the equivalence class containing BC. And then again by the definition of multiplication in Zn, the product of these two is the equivalence class containing A times the product of B and C. But this multiplication inside is just integer multiplication, and that we know is associative. So this is the same as AB multiplied by C. And then this can be split into the product of the equivalence class containing AB with the equivalence class containing C by the definition of multiplication modulo n. And this first thing is further the product of the equivalence class containing A with the equivalence class containing B. And so we have got the right hand side, and so multiplication modulo n is associative. Then you also have a multiplicative identity, which is the equivalence class containing the integer 1. Indeed, for any integer A, you have that the equivalence class containing A multiplied by this identity element is equal to the equivalence class containing A, and also in the other way. So let's quickly check this. You have that this left hand side by definition of multiplication modulo n is the equivalence class containing A times 1. But this integer multiplication A times 1 is just A, which you can also write as 1 times A, and this splits into the product of the identity element with the equivalence class containing A. And so we have got this. Now, multiplicative inverses are not guaranteed to exist. Of course, some elements may have multiplicative inverses, but in general, for general n, multiplicative inverses may not exist for non-zero elements. So here is an example. If I take n equal to 6, we know that the equivalence class of 2 is different from the equivalence class containing 0. Okay, so this is a non-zero element. But if it had a multiplicative inverse, say it's the equivalence class containing this integer A, then you would have that the product of these two is equal to the identity element, but that's the same as the equivalence class containing 2A is the equivalence class containing 1, and so 2A is related to 1 modulo 6. In other words, 6 divides 2A minus 1. But what does this mean? That means that there exists some integer m such that 6 multiplied by this integer m is equal to 2A minus 1. But I can rearrange this to read 1 is equal to 2A minus 6m, and it is clear that 2 divides this and 2 divides this, so 2 divides this thing, and so 2 divides 1. But that would mean that 2 is less than or equal to 1, which is false. And so we have arrived at a contradiction. So this element, this non-zero element, has no multiplicative inverse. Now we will see that for special n, in fact if n happens to be a prime number p, then every non-zero element in Zp does have a multiplicative inverse. Okay, so we'll prove that in a minute, but for general n's, this is not true. And finally, you have this commutativity property, which says that for any two elements, you have this thing happening. So let's quickly check this as well. So you have the left hand side by definition of multiplication modulo n is the equivalence class containing AB, but this is just integer multiplication, and we know that integer multiplication is commutative, so AB is the same as BA, so you get this, and that's actually the product of the equivalence class containing B with the equivalence class containing A. So we have proved this commutativity as well. And so far we have looked at individual properties of addition modulo n and individual properties of multiplication modulo n. And now we also have a distributive law, namely that multiplication modulo n distributes over addition modulo n. So that's the next thing we would like to prove. So here is the distributivity property, and this combines the two operations of addition modulo n and multiplication modulo n. And this says the following: if you have any three elements, then you have that the product of the equivalence class containing A with the sum of the equivalence class containing B with the equivalence class containing C is equal to, so this multiplication distributes over addition, so you can first multiply these two and then you can multiply these two and you can add them up. Okay, so let's prove this. Let's start with the left hand side. We have, by the definition of addition modulo n, that this thing is the equivalence class containing B plus C. But now, by the definition of multiplication modulo n, this is the equivalence class containing A times B plus C. But this is integer multiplication and this is integer addition, and we know that we have the distributivity law in Z. So using that, we know that this is A times B plus A times C. And now, by the definition of addition modulo n, you know that this splits into the equivalence class containing AB plus the equivalence class containing AC. And this equivalence class containing AB is actually the product of the equivalence class containing A with the equivalence class containing B, and likewise this thing is the product of these two, which is the right hand side. And so we have proved this distributivity law. So let us summarize what we have just learned. Zn is the set of integers modulo n. So it is the set of all equivalence classes under the equivalence relation of congruency modulo n. And we have just defined these two maps of addition modulo n and multiplication modulo n, and we have just learned that these maps have the following properties. First of all, addition modulo n is associative. There exists an additive identity element, namely the equivalence class containing 0. Every element in Zn has a corresponding additive inverse, and addition modulo n is commutative. Also, with multiplication modulo n, we have learned that it is associative. There exists a multiplicative identity element, namely the equivalence class containing 1, and multiplication modulo n is commutative. And the two operations, namely addition modulo n and multiplication modulo n, together satisfy this distributivity property that multiplication modulo n distributes over addition modulo n. And we also know that multiplicative inverses of non-zero elements may not exist in general. We saw an example when n was equal to 6. So Zn together with these two operations has all the properties demanded of a field, except that multiplicative inverses are not always guaranteed to exist. However, if n happens to be a prime number, then it turns out that this does form a field, and we will see that soon. But let us first see, even for general n, it may be that some elements do have a multiplicative inverse. So let's see a result about that. We will now show the result, which says that if n is any natural number and a is an integer such that a and n are relatively prime, then the equivalence class containing a is invertible in Zn. So in other words, there exists an integer x such that if you look at the equivalence class containing this x, then that multiplied with the equivalence class containing a is equal to the identity element with respect to multiplication mod n. So it is equal to this equivalence class containing 1, and since this multiplication modulo n is commutative, also you have that the product of these two is equal to the identity element. So let's prove this. What we know is that a and n are co-prime, so their GCD is equal to 1, and then we know that there exist integers x and y such that a times x plus n times y is equal to 1. In other words, the Bezout equation is satisfied with this GCD 1. So the equivalence class containing 1 is equal to the equivalence class containing ax plus ny, because 1 is just ax plus ny. And by the definition of addition modulo n, this is the equivalence class containing ax plus the equivalence class containing ny. And the equivalence class containing ax, by the definition of multiplication modulo n, is the equivalence class containing a multiplied by the equivalence class containing x. Meanwhile, the equivalence class containing ny is actually the equivalence class containing 0, and this is because 0 is related to ny under the equivalence relation of congruency modulo n. Indeed, ny is congruent 0 mod n because n divides ny minus 0, n divides ny. So this equivalence class containing ny is just the equivalence class containing 0, and we know that the equivalence class containing 0 added to anything is just the same thing, and so this is this itself. And since multiplication modulo n is commutative, this is also the equivalence class containing x multiplied by the equivalence class containing a. So we see that this equivalence class containing this x, which was produced over here, serves as the multiplicative inverse of this equivalence class containing a. So we see that if you have any element in Zn, which is this equivalence class containing a, where the a is such that a and n are co-prime, then this element possesses a multiplicative inverse in Zn. So we will now show the theorem which says that when this n is actually a prime number p, then every non-zero element in Zp possesses a multiplicative inverse. So this Zp is then a field. So let us prove that. So here is the precise statement. So let p be a prime number, and let us look at an element in Zp which is not the zero element. So let's suppose that a is an integer such that if you look at the equivalence class containing this a, that's not the zero element in Zp. So it's not the equivalence class containing 0. So then it turns out that this element has a multiplicative inverse in Zp. So there exists some integer x such that if you look at the corresponding equivalence class containing this x, then that serves as a multiplicative inverse of this element, so that when I multiply these two, I get the multiplicative identity, which is this equivalence class containing 1. So let's prove this. What we know is that this equivalence class containing a is not the equivalence class containing 0. So that means that it is not the case that a is congruent 0 mod p, because if a is congruent 0 mod p, then that would mean that a is related to 0 under this equivalence relation of congruency modulo p, and then these two equivalence classes would be the same, but we know that they are not the same, and so this cannot happen. And this inner thing means that p divides a minus 0, in other words p divides a, so that can't happen because we know that it's not the case that a is congruent 0 modulo p, and so we know that it's not the case that p divides a, so p does not divide a. And then it follows from a lemma that we had proved a little while back that the greatest common divisor of p and a is then equal to 1. In other words, p and a are co-prime. So let's quickly prove this because the proof was very easy of that lemma. We know that the greatest common divisor of p and a first of all exists because p being a prime, it's in particular non-zero, it's a positive number. So we know that this GCD exists. And this greatest common divisor is first of all a common divisor. So it divides both p as well as a. In particular, it divides p. But p is a prime number, and so the only positive divisors it has are 1 and p, and this is a positive number. So this GCD can either be p or 1. Now if this GCD is not equal to 1, then it will be forced to be equal to p. But then we have that this GCD of p and a is p, and since this GCD also divides a, then we have got that p divides a. But we know that p does not divide a, so we have arrived at a contradiction. So it can't be the case that this GCD is not 1, so it has to be equal to 1. In other words, p and a are co-prime, and so by the lemma that we just proved in the previous slide, namely this one, then we know that the equivalence class containing this element a is invertible in this Zp, and so there exists an integer x such that if you look at the equivalence class containing this x, that serves as a multiplicative inverse of this element in Zp. And so we have got this thing, and so we have proved this theorem. So this Zp with its two operations of addition modulo p and multiplication modulo p forms a field when p is a prime. So we now make the observation which says that if in Zn you have an element which possesses a multiplicative inverse, then this multiplicative inverse is unique for that element. So let us suppose that this element is invertible in Zn, the equivalence class containing an integer a, And let us suppose that you have these two which serve as multiplicative inverses. So the equivalence class containing x and the equivalence class containing y, both of these are multiplicative inverses for the equivalence class containing a, so that these relations hold. So that this multiplied by this one is the identity element with respect to multiplication, and similarly this element times this is also the multiplicative identity. Now we want to show that in fact these two are the same, that is the equivalence class containing x is the same as the equivalence class containing y. Okay, so we know that the equivalence class containing x is of course the multiplicative identity times itself, and this multiplicative identity we can write as the equivalence class containing y times the equivalence class containing a, because this serves as a multiplicative inverse of this one. So we know that the product of these two is the multiplicative identity. And now by associativity, we can combine these two so that you have the product of the equivalence class containing a and the equivalence class containing x. And we know that since this serves as a multiplicative inverse for this one, the product of these two is the multiplicative identity. But I know that the multiplicative identity times anything is the same thing. So this is equal to the equivalence class containing y. And so we have got that in fact these two are the same. So the multiplicative inverse for any element, if it exists, is unique for that particular element. So let us see some examples. Let us look at the set Z2 of integers modulo 2. Then the two distinct elements are the equivalence class containing 0 and the equivalence class containing 1. And here is its multiplication table, by which we mean that it's a table showing all the different multiplications modulo 2 taking place. So for example, the way to read this is this multiplied by this modulo 2 is this one, this multiplied by this mod 2 is this multiplied by this mod 2 is this, and this multiplied by this mod 2 is this element. And we do see that every non-zero element, well, there's only one non-zero element, namely the equivalence class containing 1, that does possess a multiplicative inverse, namely itself, because when I multiply this with itself, I get the multiplicative identity, namely this equivalence class containing 1. Now let's take another prime, say p equal to 5, and in Z5, the distinct elements are the equivalence class containing 0, equivalence class containing 1, equivalence class containing 2, equivalence class containing 3, and equivalence class containing 4. The non-zero elements are these ones, and let us show that each of them has a corresponding multiplicative inverse. Well, for 1, the multiplicative inverse is 1 itself, because the product of these two is the multiplicative identity. Then for 2, we see that the multiplicative inverse is this equivalence class containing 3, because when I multiply these two, I get the equivalence class containing 6, which is the same as the equivalence class containing 1, because 5 divides 6 minus 1, right? And so 6 is congruent 1 mod 5, and so it follows that the equivalence class containing 6 is actually the equivalence class containing 1, which is this multiplicative identity. And similarly, since multiplication is commutative, also it follows that the multiplicative inverse for this element is then the equivalence class containing 2, because the product of these two is the multiplicative identity as well. And the multiplicative inverse of this non-zero element is itself, because the product of these two will be the equivalence class containing 16, which is the same as the equivalence class containing 1. Indeed, because 16 is congruent 1 mod 5, because when I take 16 minus 1, I get 15, and 5 divides this. Okay, so in this case, we see that each of the non-zero elements does have a multiplicative inverse, as was promised by the previous theorem. Okay, so let's look at this example, which is a theoretical example, and in this example, we will determine which are the elements in ZP whose square is the multiplicative identity, and P here is a prime. And we'll see that the square of an element is the multiplicative identity if and only if the element is either the multiplicative identity itself or the equivalence class containing P minus 1. Okay, so let's state our claim precisely. Suppose that P is a prime, then ZP we know is this set consisting of these P distinct equivalence classes. And let's suppose that A is a number which is in between this 1 and P minus 1. Okay. Then our claim is that the square of the equivalence class containing A is equal to the multiplicative identity in ZP if and only if this element is the multiplicative identity or this element is the equivalence class containing P minus 1. Okay, so there are two implications that we have to show over here. Let's start from this one and prove that this holds, and then we will also start from here and prove that we have this. Okay, so let's start with assuming that the equivalence class containing A is either the multiplicative identity or the equivalence class containing P minus 1, and let's show that then this element has a property that when you square it, when you multiply it with itself, you get the multiplicative identity. So of course, if you start with this, then its square is this multiplied by itself, and since this is the multiplicative identity, this is of course equal to the multiplicative identity. And now let us look at the case when this element is the equivalence class containing P minus 1. Now first of all, let us note that this equivalence class containing P minus 1 is actually the equivalence class containing minus 1, and the reason is because P minus 1 is congruent minus 1 mod P, and the reason is because when I subtract from P minus 1 this integer, so if you do P minus 1 minus minus 1, then this becomes plus 1, so that you end up with P, and P of course divides P, and so it follows that P minus 1 is congruent minus 1 mod P, so that these two equivalence classes are the same. So when you want to square this, okay, let's note that this equivalence class we have just observed is the equivalence class containing minus 1. So I'm multiplying this with itself, and by the definition of multiplication modulo P, this is the equivalence class of the integer minus 1 times minus 1, which is of course plus 1, and so you get the multiplicative identity. So if this holds, then certainly this holds, and now let us start from over here and show that one of these two has to hold. If you have that the square of something is the multiplicative identity, let's note that if you have the equivalence class containing A square, that's the same as the equivalence class containing A multiplied by itself, so A square. And since these two equivalence classes are the same, this means that A square is congruent 1 mod P. That means that P divides A square minus 1. But A square minus 1 factorizes as A minus 1 times A plus 1. And since P is a prime and it divides the product of these two integers, it has to divide at least one of them. So in the case when P divides A minus 1, this is the same as saying that A is congruent 1 mod P. After all, what does this mean? This means that P divides A minus 1, which we have. So you have this. And now since A is related to 1, it follows that their equivalence classes are the same. So the equivalence class containing A is the same as the equivalence class containing 1. So then we have this. And in the case when P divides A plus 1, then that's the same as saying that A is congruent minus 1 mod P. After all, what does this mean? This would mean that P divides A minus minus 1, which is A plus 1, which we know is true. So we have this, and so A is related to minus 1 under this congruency relation mod P, and so the equivalence classes are the same. So it follows that the equivalence class of A is the same as the equivalence class of minus 1, and we had just seen that the equivalence class of this minus 1 is the equivalence class containing P minus 1, and so we have got this. So if this holds, then we have also seen that this statement holds, and so we have proved our claim. Now we will use this claim to prove a number theoretic result which is known as Wilson's theorem. Okay, so we will soon prove Wilson's theorem, but first let us derive some corollaries of the result that we have just shown. So let's recall that what we have shown is that in ZP, the only element whose square is the multiplicative identity is this element or this element. And let's note that saying that the square of the element is equal to the multiplicative identity is the same as saying that the only element whose multiplicative inverse is itself is either this one or this one. Okay, So we'll use this to first of all derive the following corollary, which says that if P is a prime number which is strictly bigger than 3, then the product of these elements is equal to the multiplicative identity in ZP. So let's prove this. Now first of all, let us notice that since P is a prime which is bigger than 3, it is odd, and so P minus 2 is also an odd number. And if this product would have begun with the equivalence class containing 1 all the way up till P minus 2, then there would be an odd number of terms. But since this equivalence class containing 1 is missing, from an odd number of terms, we are taking away 1, so this will contain an even number of terms. Also, let us note that in this product, the equivalence class of 1 does not appear and the equivalence class of P minus 1 does not appear. But those were the only elements whose multiplicative inverse was itself. So if I take any of the remaining equivalence classes in this list over here, then it will have a multiplicative inverse which is not itself but will appear somewhere else in this list. The multiplicative inverse of any of these elements is of course not equal to 1, because any of these elements multiplied by 1 will give that element itself, which is not equal to 1. And the multiplicative inverse of any of these elements is not the equivalence class containing P minus 1 either, because if that were so, that would mean that the multiplicative inverse of P minus 1 would be one of these elements, but we know that the multiplicative inverse of P minus 1 is itself, and we know that multiplicative inverses are unique. So the multiplicative inverse of each of these elements, which does exist, has to again appear in this list because it can't be 1 or P minus 1. Okay, so each term in this product has a corresponding multiplicative inverse which is not itself, and it appears somewhere in this list. So each element in this list has a corresponding multiplicative inverse, and so the terms, they pair up, and the product in each pair will be the element together with its multiplicative inverse, giving rise to a 1, the identity element. So let's see a concrete example. If P is the prime number 7, then this product has these 4 terms, and the terms pair up like this. So the equivalence class 2 has as its multiplicative inverse the equivalence class containing 4. Indeed, the product of 2 and 4 is 8, which is 7 plus 1. And so the product of these two is the equivalence class containing 1. Similarly, the product of 3 and 5 will be 15, which is 14 plus 1. And so this element serves as the multiplicative inverse of 3. And so we have that the product of these 4 elements is really the product of these two and the product of these two. In each case, you get the identity element, and the product of these two is equal to 1. So as another concrete example, let us take P equal to the prime number 11. And now P minus 2 will be 11 minus 2, which is 9. So this product will start from 2 and will go all the way up till 9, giving rise to these 8 terms. And again, the terms pair up. For example, the multiplicative inverse of this element will be the equivalence class containing the number 6, because the product of these two will be 12, which is 11 plus 1. So the product of these two will give rise to the identity element. Similarly, 3 pairs up with 4, their product is 12, which is again 11 plus 1, and so that gives rise to an identity element. And for this element 5, it pairs up with the equivalence class containing 9, because the product of these two will be 45, which is 44 plus 1. So the product of those two will also give rise to an identity element. And finally 7 pairs up with 8, because their product is 56, which is 55 plus 1. So these two pair up to give the identity element as well, and the product of these 4 is the identity element. So just as in these two examples, in general too, the terms pair up to give an identity element. Now since there are an even number of terms, if for example I take 2 and that will combine with its multiplicative inverse giving 1, and if I remove these two elements, you are again left with an even number of terms. Now if I take any element from this remaining list, it will have its multiplicative inverse, which again appears in this list, because it cannot be 2 or the multiplicative inverse of 2, because multiplicative inverses are unique. So the multiplicative inverse of anything in the remaining list will again appear in the remaining list. And in this way, all the terms pair up and you get the identity element. So now we have proved the corollary, which says that if p is a prime number which is strictly bigger than 3, then this product is equal to 1 in ZP. So now let us prove a further consequence of this result, and this is essentially Wilson's theorem. And this says that if I take the product of all the non-zero elements in ZP, so I'll take the equivalence class containing 1, equivalence class containing 2, and all the way up till the equivalence class containing p minus 1, if I take the product of all of these, then this is equal to the equivalence class of minus 1 in ZP. And now this works for any prime p, so the qualification that p should be strictly bigger than 3 has been removed. So let us prove this now. So let us first get rid of the cases when p is equal to 2 and when p is equal to 3. Well, when p is equal to 2, this p minus 1 is equal to 2 minus 1, which is 1. And so this product just collapses to 1. And that we want to show is equal to the equivalence class containing minus 1 in Z2. So is that true? Well, in order to prove this, we need to check that 1 is congruent minus 1 mod 2. In other words, 2 should divide 1 minus minus 1. Well, 1 minus minus 1 is of course 2, and 2 does divide 2. So these two are indeed equal. So when p is equal to 2, this is indeed true. And what happens when p is equal to 3? Well, in that case, this product starts from 1 and goes all the way up till 3 minus 1, which is equal to 2. So this product has just two terms, which is the equivalence class of 1 multiplied with the equivalence class containing 2. And the product of these two, by definition, is the equivalence class containing 2. And that we would like to show is equal to the equivalence class containing minus 1. Well, to prove this, we need to check that 2 is congruent minus 1 mod 3. And that is indeed true because 3 does divide their difference. Their difference is equal to 3 and 3 does divide that. And so we have that these two are equal, and so this product is indeed equal to minus 1 in Z3 as well. So for p equal to 2 and p equal to 3, this result is true. And now let us prove it for p which is strictly bigger than 3 by using this result. Now this is just the identity element, so it is enough to calculate what this is. And if p is bigger than 3, we know that this product is equal to 1. So we know that this product is equal to 1. So it suffices to just prove that this is equal to the equivalence class containing minus 1. But that we had seen earlier, and that is clear because p does divide the difference of p minus 1 and minus 1. Indeed, p minus 1 minus minus 1 is p minus 1 plus 1, which is equal to p, and p does divide this. So this equivalence class is the same as this one, and so this whole product is just the equivalence class containing minus 1. And so we have proved this corollary for all primes p. So we'll now show Wilson's theorem, which is a certain number theoretic result, and this Wilson's theorem is really a translation of what this corollary says. So first of all, Wilson's theorem says that if p is a prime number, then p minus 1 factorial is congruent minus 1 mod p, or in other words, p divides the difference of these two integers. So in other words, p divides p minus 1 factorial plus 1. So let us prove Wilson's theorem. Now we know this corollary, and the left hand side over here is the product of these equivalence classes. But by the definition of multiplication in ZP, we know that this is the equivalence class of the integer which is the product of all of these integers 1, 2, 3 all the way up till p minus 1, in other words p minus 1 factorial. So this left hand side is the equivalence class of the integer which is p minus 1 factorial, and that we know is equal to the equivalence class containing minus 1. So in other words, p minus 1 factorial is related to minus 1 under the equivalence relation of congruency modulo p. So we know that p minus 1 factorial is congruent to minus 1 modulo p, but that's the same as saying that p divides p minus 1 factorial plus 1. So this proves Wilson's theorem, and this finishes chapter 5. So let's see what we have learned in chapter 5. So chapter 5 was all about the set of integers with its two operations of addition and multiplication. We began the chapter by learning about this division algorithm, which is a theorem which says that any integer can be divided by a non-zero integer, and in the process we get a quotient and a remainder, and the remainder is an integer which is bigger than or equal to 0 and strictly less than the modulus of the number with which the division is taking place. Then we discussed divisibility, and then we also introduced the notion of the greatest common divisor and learned about Euclid's algorithm for the computation of the greatest common divisor. Then we defined what primes are and learned about the fundamental theorem of arithmetic, and we saw also how using the prime factorization you can compute the GCD. And finally, the last topic in chapter 5 was on this modular arithmetic. We introduced an equivalence relation which is congruency modulo n, and then we introduced the notion of addition modulo n and multiplication modulo n, and we learned some properties of these operations. So that was a quick recap of the topics that we learned in chapter 5, but let me also give you a quick overview of what we have learned in MA 103 in my part. So in the first 5 weeks of Michaelmas term, which were not given by me, you learned about sets, functions and logic essentially. And then in the last 5 weeks of Michaelmas term, which were given by me, we learned about the foundations of analysis. So we basically covered 3 topics, chapter 1, 2 and 3 from my lecture notes. In chapter 1, we began with a discussion of the real numbers, and in particular we learned this very important property for doing analysis, namely the least upper bound property of the set of real numbers. Then in chapter 2 we discussed sequences and their convergence, and in particular we learned about theorems which tell us how to deduce convergence based on the properties of the sequence. For example, we learned that monotone and bounded sequences are convergent. Then in chapter 3, we discussed continuity of functions, and we first gave the definition of what it means for a function to be continuous at a point and on an interval, and then we learned about properties of continuous functions. For example, composition of continuous functions is continuous, and we learned other things, for example, the intermediate value theorem and the extreme value theorem. So that was essentially what we did in the Michaelmas term. And then in the Lent term, in these first 5 weeks, we have covered chapters 4 and 5 from my lecture notes. In chapter 4, we looked at number systems. We started with the set of natural numbers. From there, we constructed the set of integers, and then the rational numbers, and finally the real numbers. And in each of these cases, we introduced the operations of addition and multiplication, and also the order relation, and we proved things like the associative law, commutative law of these operations, and the trichotomy law and so on. So the familiar arithmetic rules were all proved. And in the case of real numbers, we also know that it has this very important least upper bound property of the real numbers. Then also in this chapter 4, we also discussed what is the set of real numbers which are not rational, so the irrational numbers. And we learned this important rational zeros theorem, which gives us a tool of sometimes proving the irrationality of some real numbers. And we also showed that the Euler constant E is not a rational number. And the last part of this chapter was on cardinality of infinite sets, and we discussed countable and uncountable sets. And we have spent some time covering chapter 5, so this is fresh in our minds. Now in the last 5 weeks of Lent term, which won't be given by me, you will learn about groups and vector spaces. Okay, so that's it from me as far as the online lectures go, but of course we will meet again during the question and answer session.